had gone over some of this on Friday before I had given you the problems that you were going to do, the extra practice problems. And let's remember that on Friday, what we really worked on kind of setting and differentiating is the two different kinds of trials. You can have a trial where they say, boom, look at 5. Boom, look at 6 items. So look at 6 items over and over and over and over again. Look at 8 items over and over and over and over and over again, or whatever. So they give you a set number with which to look at. And if that's the case, then with your trial, you're saying yes or no, you achieved what you were trying to achieve. Versus the other possibility for a trial is go until something happens, and then if that's the case, you count how many it took for that success to happen. All right. Now, I think we had already kind of talked about this number 1 on Friday. This was a go until. This was a go until you get your sum of 300, and then we did that, and you did have to ignore repeats on this one, because once you had a person win, once a coupon winner won, that coupon winner was not allowed to win again. All right. This problem, however, was not a go until. This problem was a dig 8 mines. So set of 8, set of 8, set of 8, set of 8. And your trial was based on looking at 8 mines, and the repeats are okay because it was just keeping the same probability. And the probability is based off, so these numbers that you set things to be are based off of the probability that they tell you. So the 10% mines is what set this part right here. Okay, the 10% mines is what set the each one-digit number and let the number 1 be whatever. Okay, so because this was out of a set number of mines, then your response was yes, no, whatever it was happened. And in this case, exactly 3 happened. Yes or no, exactly 3 happened. Okay, now, I wanted to show you this for the exactly 3. I think I kind of did talk about this on Friday, but I wanted to reiterate where this is on the formula chart. Okay, so on your yellow formula chart, on the right-hand column, see, we're going to be using almost all of these ones over here on the right-hand column. This is the formula to do that, and so then in this case it was find the probability that you have exactly 3, and so it was out of 8 things, choose 3. Okay, P was the probability of success, which the probability of finding a gold mine was 0.1, and we wanted to have 3 gold mines. And then the failure would be what's left, which is 0.9. And if you have 3 gold mines, then there would be 5 without gold. So that's the formula that you do, and then you put this into your calculator, your binomial PDF of NPK. All right, and so what was different about this second one here is you had 2 items. You had to do the PDF of 0 plus the PDF of 1, and you could do 2 calculator strokes. You could do PDF of 0 plus PDF of 1, or you could save some calculator strokes and do the cumulative up to and including 1. So that way in one calculator stroke, it gives you the PDF of 0, binomial PDF of 0 plus the PDF of 1 in the cumulative up to and including 1. Okay, now let's talk about what this means. Okay, because I really want you to be able to kind of interpret these histograms. So here we go. So this was 100 trials were run where they figured out the number of mines that were dug until you find one with gold. So let's look at this. This situation means 6 times they had to dig one mine and found gold. Okay, let's look at this one. This one says 5 times they had to dig 9 mines in order to find gold, and so on. And looky here, all the way down here, 2 times they had to dig 30 mines in order to find gold. Okay, so to average that, you're actually doing your frequency times how many mines they had to dig, plus the next frequency times 2 mines, plus 9 times 3 mines, all the way up to the 2 times 30. Divide it by 100 so that you get an average, and it comes out to 10.39. Now, can I have an unrealistic number like that for this value, this expected value? Yes, you can, because it is a mean. And that's on average how many mines you expect to have to dig in order to get one with gold. Now, you didn't have to know this, but I wanted to remind you that the expected for geometric probability, I have it here, is 1 over P. 1 over the probability of success. And the probability of success was 0.10, which meant on average they'd expect you in the long run to do 10. Why is this one off? Why is this off a little? Because law of large numbers, this is like experimental. This is getting closer, but we've only done 100 trials. This is what's going to happen as you get to infinity number of trials. Okay. All right, good. All right, now, I really want you to understand this one, so I'm going to take you through it so that I can get you to understand Part C. Understanding Part C is important. So, let's take a look here and understand this. All right, first of all, you have this problem about the amount of active ingredient in these pills. Okay, so it has been determined that if there's a tablet with fewer than 8,500 units of active ingredient, then there will not be, it will not relieve the symptoms. So, determine the probability that you find a caplet, so one caplet, with less than 8,500 units of medicine. Okay, round your answer to the nearest tenth. So what happens is, because you have the mean of 9,000 and the standard deviation of 590, you can do the normal model here. And so here is a tablet. So inside here is individual tablets. And this is a tablet or something less. And that probability would be finding that z-score of 8,500 minus 9,000 over 590. That z-score is negative 80.8475. So that z-score is 0.1984. So when it says to round to the tenth, that's 20%. So in essence, about 20% of the tablets have insufficient amount of active ingredients. Less than 8,500. About 20% have an insufficient amount of active ingredients. Okay. Then, based on that 20%, you're asked to run the simulation. So, each one-digit number represents a tablet. Let the numbers be. So, because of this 20%, I let the numbers 1 and 2 represent a bad tablet, and the rest are okay. Use the random number table. Start at the top left corner, the second one or the one down below. Okay, this is going to be, this says says run 5 simulations for the number of tablets the lab technician samples before finding 3 with less than 8,500 units. So is this a look at a set number of tablets or a go until problem? It's go until. Go until what? 3 bad ones. So here, I go along here until I find 3 1s and 2s, and then I stop. And my response is how many tablets I examined to do that. And the first was 14. This trial I had to examine 8. This trial I had to examine 15. This trial I had to examine 21, and this trial I had to examine 26. So on average, I had to examine 16.8 according to my simulation. On average, the lab technician would have to examine about 16.8 to find 3 without sufficient medicine in them, okay, that are bad. Okay, now, hopefully you kind of follow that, because that leads us to the top of the next page, which is these histograms here, and this is what I really wanted to go on. So, draw these lines in here. I think it makes it easier to understand if you haven't on your homework too. Draw those lines in there. Okay? Those green lines to make it look more like a histogram. Okay, and so then we're going to talk about what's going on here. Okay, so first of all, these are both 100 trial simulations where the lab technician was looking for 2 tablets. One situation is, did you stop when you find 2 tablets that are less than 8,500, and then the other picture represents stop when you find 2 tablets that are greater than 9,000. Okay. So, by looking at these pictures, what can you tell is like a key difference between these 2 pictures? They both had 100 trials. What did you say?
There's 2 outliers.
Okay, over here, well, the key to me drawing an arrow here is that it's more stretched out. Do you see this is going from 2 all the way up to 24? You know, and maybe those are outliers, I don't know. And this one's just going to 14. So these are definitely having some goals are taking longer to achieve. Do you see that? So up here, this number 24 right here means that the lab tech had to look at 24 tablets to get 2 successes. Whether that is less than 8,500 or greater than 9,000, we still have to determine it. So why do you think some of these would have to go all the way out to 24 to happen, and this one only had to go out to 14? What's the quality of this set here since it takes longer? Okay, how do you know? You mean it doesn't tell you which one's which? Okay, but why is this distribution spread out and have ones that take longer? Okay, why? Thank you. These events, the events that happen on this one are less likely to occur than the other side. So because these events are less likely to occur, they are taking longer and hence spread out. These happen faster, and because these are more likely to occur and they happen sooner, then these bars are higher. Okay, so now we already know less probability of finding one of them that is less, finding one that is less than 8,500 is 20%. Now this isn't about two, but we know just individually finding one that has less than 8,500 is a 20% chance. So let's think, what's the probability of finding a tablet greater than 9,000? What's that one? Oh, you know what? It's not 80%. Greater than 8,500 is 80%. Yeah, but I boobied on that right there. Greater than 8,500 is that. What is the probability of greater than 9,000? How much? 50, because 9,000 is the mean, so greater than 9,000 is 50%. So the probability of finding one greater than, so that happens easier. So therefore, which is this one on the left? The one that's greater than 9,000. And this one on the right is the one that is less than 8,500. Okay? This is supposed to be actually 50. 50%, you will get two of them sooner than getting two of the other type of tablets. Okay, so that's the key there. All right, now, in class on Friday, you guys were able to do a lot of these. Let's check those real quick. Anybody need to get those? Did you get those that were absent? They should have been on the thing. Huh.
The video, there's where you're going over like the beginning. No, I have those.
Oh, I didn't have these.
Yeah, I have these. Like
Okay,
I
sorry,
got them
I'm
off
back.
the internet, but like you didn't go over them in the video. So.
Okay. Yeah.
Like, it just stopped whenever you were introducing.
Gotcha. Gotcha. Right. I didn't go over them in the video. See, look here.
Yeah, I got those.
Okay. I put that Friday afternoon.
Oh, okay, that was good.
So that would have been one. Yeah. Because I kind of changed the lesson plans after Friday because of how many people were gone and stuff. So that's okay. But anyway, so here we go. I'm just gonna kind of let you guys look at these real quick. Number 2 is interesting. I want to talk about that one. Goes until you get a Tiger Woods. So since you go until you get a Tiger Woods, and the repeats are okay and one digits are okay, then the response is how many boxes of cereal you had to pick. Okay, so it looks like this when you look at the back. Not a Tiger Woods, not a Tiger Woods, Tiger Woods. So that took 3 boxes of cereal. Not a Tiger Woods, not a Tiger Woods, not, yes. So that took 8 boxes of cereal. Okay, and so on. And then you averaged it, and I got an average of 4.9. Well, the thing that's interesting about this average of 4.9 is that if you actually do the expected, which is 1 over P, what's the probability of Tiger Woods? 20%. And what's 1 over 0.2? 5. So in theory, 5 is how many you should have to look at to find one that has Tiger Woods. And look at what our simulation gave us, 4.9. So it's close. Okay, so that's nice. All right. Let's look at number 3. Number 3 was a straight look at 6. Look at 6. Look at 6. Look at 6 multiple choice questions. So that was a look at that many, and then your response is yes or no. You got all of them correct. Okay, that's what number 6 asks. So you look at 6, look at 6, look at 6, and your response is yes, no, that you got all 6 questions correct. And then this 80% chance, what is this 80% chance of getting them all right plays into your let each digit represent, a question. And your 1 through 8 gives an 80% chance of getting it correct. Number 9 and 0 were wrong. Okay, so when I went and did my simulation, simulation over here, I drew a line every 6 problems. Every 6 problems. I drew a line every 6 problems. And I was looking for all the numbers being 1 through 8. If I saw a 9, that means I missed one. A 9 or a 0, I missed one. So they were not all correct. There, I got 2 wrong. There's 1 wrong. There's 3 wrong on that one. 2 wrong, 3 wrong actually. So I got, according to this simulation, 7 out of 20 correct. Or, no, that's wrong. 7 out of 20 sets of 6 multiple choice questions, I would have gotten all of them right. Yes.
Does it matter which numbers you use for the left?
No, it does not. You may get something a little different. What did you use?
I used 0 and 7 for the answer correctly question.
Okay. And what did your percent come out to be?
Mine was like 8 out of 20, so it's like 40%.
So it's close. All right, so that's good. So it still comes out close. Mine was 35%, and when she used 0 to 7 as her correct answers, hers was 40%, so still pretty close. All right, so according to my simulation, I expect to get all 6 multiple choice questions correct about 35% of the time, on average. All right, let's talk about this last one. Okay, here we go. First of all, because this says 34% of the candidates, you have to use 2-digit numbers. Okay? So each 2-digit number represents a driving test. All right. Now, next, it said the first time you take the test, it's a 34% chance of passing. Okay? So what that's saying is this. Let's just say we got 2-digit numbers going along. Okay? And I will stop once I pass a driving test. So you will look at this first event of taking the test and which values will represent passing that first test. I set numbers 0, 1 to 34. So if I get a 0, 1 to 34, then I pass that test and I'm done. Okay? But what happens if I don't pass that test? Then I got to keep going. So if I don't pass that test, so say that ended up being something out of the range, then I look at the next test, and what's the passing rate for that test? 72% chance, so I chose 0, 1 to 72. So now on all of these subsequent tests, the rule is 0, 1 to 72 represents a pass. And I go until I find a pass. Okay? So then that will tell you how many tests had to be taken. Say this was a 83. Is that a pass yet? Nope, still haven't passed. Let's say 68. How about that? Yes, that is a pass with the rule here. So it took 3 driving tests for that person to pass. And that's the response. Okay, yes. Is that good? All right. So, ta-da. So when I did that, there's my numbers, looks like that. And so on average, according to my simulation, I expect a driver to have to take about 1.8 tests to pass on average. Okay, ta-da, done with that. So your FRAPPY was an actual number 6 on the free AP response problems, okay, way back in 98. So that was a long time ago. So I honestly think this is probably a little easier number 6 than they kind of have gotten a, that the test started in 97. So they were still kind of playing around with kinds of things they expected people to know and at what difficulty level. I think this is probably a pretty easy, straightforward number 6, especially in part A. I mean, it was pretty simple that the Z-scores were a half down and a half up. So at first, You were trying to find 2 pearls that were acceptable. And you wanted them between 7 and 9 millimeters, and all of them are distributed to have a mean of 8 and a standard deviation of 2. So, for part A, you had to find the probability of getting an acceptable pearl. And it specifically says to express your probability as a number between 0 and 1 and round the probability to the nearest tenth. So when I did norm CDF from negative 0.5 to positive 0.5, I got 38.29%, but it said express as a decimal between 0 and 1 and round to the nearest tenth. So that tells me I'm going to use this or work this simulation with a probability of 40%. Okay? So they were specific on how they wanted you to do that numbers because it actually then made part B much simpler. Then when we got to part B and we run a simulation, I can use 1-digit numbers. Okay? So 1-digit numbers with 4 of them representing an acceptable pearl. And the rest, 5 through 9 and 0, I said is an oyster without a good pearl. I used the random number table on the back and start at the top left corner. Trial consists of, we are picking, what did they want us to do? Describe how you would use a random number digit to carry out a simulation to determine the number of oysters needed to find 2 pearls of the appropriate size. So I'm going to pick what? A set number or pick until. Pick until. Pick until you get 2. So my trial is picking 1-digit numbers until I get 2 pearls of the appropriate size. So if I'm picking until, then my response is how many I had to pick, how many oysters I had to look at to get 2 acceptable ones. How many oysters I had to look at to get 2 acceptable ones. And how many oysters I had to look at to get 2 acceptable ones. So that's my response, is how many I had to look at to get 2 acceptables. Then, after I did actually the next part, I did that, and so according to my simulation, I expect to pick about 6 oysters to find 2 of the appropriate size pearls. Okay. So C says that C was where they just wanted you to show marking on stuff and everything. All right, now look at this one here. This is like those problems that showed up on your homework part 2. Okay? On your homework part 2. So let's examine these problems. What do you see about the relationship of the bars between distribution A and distribution B? What's going on with that? Okay, well, B looks like it has a lot more bars. Why? They both open. Oh, okay, I see. Yes. More oysters had to get opened. This is one. Each of these represents 100 trials. But look, on distribution B, there was one time they had to open 29 oysters in order to find 2 pearls of the size they were looking for. Okay? This one, the worst was they only had to open 14 oysters to find the pearls that they were looking for, the 2 pearls they were looking for. So your choices are 2 pearls between 7 and 9, and I know the probability of one of them between 7 and 9 is, so I know the probability of one of them between 7 and 9 is 40%. How did I figure out this? The probability of one oyster between 4 and 6.5. How did I figure that out? I did another normal model. I did the z-score for 4, I did the z-score for 6.5, and that was a 20% chance. So, which one of these is going to be the one with the smaller probability? Good. Distribution B is the one with the smaller probability. Distribution A is the one with the larger probability. So the question is, which one is 7 to 9? That's the 40%. So it's distribution A represents the search for two 7 to 9 millimeter pearls, since the probability is higher for that 7 to 9 than the probability for this between 4 and 6.5. The events happen sooner and with less variability. Okay? Use the appropriate distribution to compute an estimate of the expected number. So you can do this: 9 times 2 plus 22 times 3 plus 30 times 4 plus 12 times 5 plus, and so on, divided by 100. Now, let me show you something real quick on your calculator, how you could have done that, okay? If you're interested in knowing this handy-dandy shortcut, let me show you. If you put the number of oysters you had to pick in list 1, so I'm actually going to do 1 up to 15. Let me enter in my numbers there. And then in list 2, put how many times those happen. So in list 2, put the frequency. So when I go here, and I go put some information in my list, okay, so I'm going to do 0, I actually probably didn't have to do all of those. So what's the probability of 0? I mean, how many times was 0 opened? Yeah, I kind of didn't have to do that. How many times was 1 pearl opened? 0. And then 9, 22, 20, 12, 13, 6, 6. So these are the frequencies. Okay. So again, these are the frequencies. So I can go stat over to calculate the one variable stats. But here's the key that I've never shown you. You want to calculate the mean number of oysters opened, and I put that in list 1. Okay, fine. But I put it in there with list 2's frequency. So see, I go comma, list 2. Then what that's going to do is have 9 2's, 22 3's, 20 4's, and so on. And so then I hit enter, and that comes up with the overall average. See, look, it's the same, 5.16. Going 9 times 2 plus 22 times 3, and so on, and averaging those 100s. So again, here's how I did that. Stat, over to calc, one variable stats. It is just one list I'm calculating. List 1 with list 2's frequencies. And that's how I got it. Okay, ta-da. That's that. What else happened on here? Okay, so according to the Hunter's House, it will take about 5.16 oysters on average to find 2 appropriately sized pearls. All right, so that was a Big Daddy number 6 on the AP test. You know, you have 5 that are kind of regular, and then number 6 takes you above and beyond what you do in your normal everyday learning. Okay, so what you are going to be doing is turning in with your take-home quiz those items that I had put up here at the front. So what you will be turning in again tomorrow with your take-home quiz that I'll give you here in just a second is the Chapter 11 Homework Part 1. which doesn't say homework part 1, it just says random number table problems. Homework part 2 that we just went over, the extra practice that we just went over, and the FRAPPY that we just went over. So those 5 things will get turned in tomorrow. Those 4 things get turned in with the quiz, making it a total of 5. All right, so let me hand you that, and you guys can get started on that somewhat.